We're going to be looking at exponential graphs today. This is section 4.1. What you see here, y equals a times b to the x, is your generic form of what an exponential equation would look like. Some number times another value raised to a power. What's important here is we label a few things. This is called the growth factor. I hope you're taking notes. Okay, you have the growth factor. Notice that your variable is in your exponent. This must happen. So this is the variable being in your exponent kind of defines what we're looking at today. This is basically exponential growth. We're going to look at that. Then we'll take on a little bit later exponential decay. We want to kind of talk about a few things first. How, if I were to look at this, if I had a generic equation with some actual numbers, then how would I know if it's growth or how would it be decay? And so this is what we look for. If a, the number out front, is greater than 0, and, so two things have to happen, and b is also greater than 1, then it's exponential growth. And in terms of just defining things, how they look, what they are, this is it. You have an equation. It's going to be some number times b to which would be a number. So, for example, we could have something like this: y equals 2 times, let's see, 2 times, say, 3 to the x. And that's a basic exponential equation. Something that, and we are really going to focus on the graphs, so be aware of that. Something that you're going to look at. Exponential growth happens to look like this. Population growth, bacteria growth, all that stuff is going to be, well, if I can just quit doing that. That's what you're going to have. That's the basic shape. And the parent graph for these is, there's not just one parent graph. Like with all the other graphs, x squared, that was the parent graph for quadratics, x cubed, and here it's going to x cubed, or let's say 3 to the x could be parent, 4 to the x could be a parent. So that 3, be careful. That's not a stretch or a shrink or anything else. Okay, the number out front, now that definitely does stretch or shrink, depending if it's a big number or a smaller number. That does. But the number inside, this number will never come into your description of what happens in terms of the changes on your graph when we talk about transformations. So let's go ahead and graph. Let's go graph one of these things. So y equals 2 to the x. We'll just let the a in this case is 1. B is equal to 2. So my a is greater than 0, and my b is greater than 1. So we have an exponential growth function. Let's go ahead and graph this function. I want you to pause the video, and I want you to graph this on your own. I want you to plug numbers in. Do what you can. If you have to get a calculator out, fine, but be smart about it. Choose numbers that you know would work well. Like 2 to the first power is really easy. So if I plug in 1 for x, then y is going to be 2. 1 or 2 to the first power is just 2. There's a couple of numbers, and you'll get used to this. There's a couple of real easy numbers, and we'll talk about it. So pause the video and try to graph that real quick. Take about 2 or 3 minutes. What we're going to look at is, first things first, x and y table. The easy choices are going to be this: -2, -1, 0, 1, and 2. Which is plenty of points. I mean, you have 5 points. That's a little bit overkill. We don't need all those points, but this will give me a really good idea of what's going to happen. When I plug -2 in, you got to remember that that's a negative exponent. So that's going to be 1 over 4. Negative 1 is going to be 1/2. 0, we said earlier, well, we didn't say earlier, anything to the 0 power. For example, in this case, 2 to the 0, that's always 1. I don't care what the number is. If you raise it to the 0 power, you got 1. If you raise it to the first power, that's easy. That's 2, and 2 squared is, of course, 4. Notice that you have inverse, or the reciprocal, of the numbers across from 1. If you remember negative exponents, remember these x's are going to end up being exponents. So when you have 2, so let's say to the negative 2, we got to get rid of the negative. So that's going to be 2 over 2 squared, which ends up 1/4. So that's how we get the fractions, and of course 2 to the negative 1 is just 1/2. Let's go ahead and plot these points. Let's see if I got enough space. We'll get close. So I have, it does not let me draw points. There's a point. Let's go over to negative 1, that's 1/2. And then 1/4 over at 2. Seriously? There we go. Over at 1, it goes up to 2. Over to 2, 1, 2, 3. We'll just say it pretty close. That's not exactly 4, but you get the idea of what the point of what the graph looks like. So we draw in the curve. You got it here and here. Something to note, this graph has an asymptote. When you look at asymptotes, make sure you never cross them. On a graph, if you cross an asymptote, even if it's an accidental crossing, you will lose credit for that. An asymptote can never be crossed under any circumstances, especially vertical asymptotes. Okay, for horizontal asymptotes with exponential graphs, we're not going to crossing these either. So you've got a couple of parts. What did I graph? I wanted to graph the y-intercept. That's important. I needed to graph the horizontal asymptote. And to start with, your horizontal asymptote is always going to be y equals 0. And we're going to look at an example in just a second. What happens when we change the graph? What happens when we transform it? We add something, we move it left or right, or we stretch it. What happens to the graph in that case? Not hard to decide, but you're going to have to make sure to watch out for those kind of things. You don't just assume that it's always y equals 0. When in doubt, plug in points, kind of like what we did here. You're going to need to know that the horizontal asymptote is y equals 0 to start with. Your vertical shift, that goes up or down, your asymptote follows that vertical shift. We'll look at that in just a second. If you need to rewind and watch this a second more, please feel free to rewind and graph this. Remember, you wanted to be able to graph this equation by yourself. You don't want to have to copy it from me. Example 3. Let's look at a transformed graph. So let me give you the basic function. So it's a b to the x minus h plus k. This is exactly what you're used to. This is a stretch or shrink. H, kind of get out of the way. H goes left to right. If it is plus, it's going to go left, and if it's minus, it goes right. K, it's up and down. No biggie there. I mean, this is what you've been seeing. If K is plus something, it's up. If K is minus something, it's down. Just like you've always looked at it. Okay, so let's look at a real example. This is going to be y equals 3, 2, x plus 1, plus 2. So if we were just to describe this, well, first of all, it's been stretched vertically by 3. compared to the parent function here. It's just going to be y equals 2 to the x. So how has it changed from that parent? Remember, your parent is always going to take a form of your base, and the base here is 2. So it's easy enough to see that this is going to go to the left 1, it's going to go up 2, and it's going to be stretched vertically by 3. And it would be easy to just move the graph of 2 to the x, which we already graphed. It's easy just to take that, move it left 1, up 2, but with that stretch, I'm going to really need to plot a few points. And I really don't need to plot that many. In fact, I could probably get away with just 2 points, as long as I remember the asymptote. And that is right there. Y equals 2 is going to be my asymptote. Let me draw that. Alright, here we go. Now I'm not going to let my intervals end up being 1. I'm going to kind of estimate them. What we look at, we're going to have, I'm going to go ahead and draw in my asymptote. We'll let each of these things be 2. Just to kind of make up for it. That's 2 and 4 and 6. So if I have a horizontal asymptote at 2, we'll go ahead and draw that one in. If I want to know where it is on the y-axis, because one of the things I look for is the y-intercept. I'm going to go ahead, plug 0 into the equation. Let's just work that out. So that's going to be 3 times 2 plus 2, which is 8. So we'll go all the way up to 8 here. Put the point there. Draw that all the way up. The next one we're going to do, I'm going to go ahead and I'm going to plot, let's say, -1. So we'll come back and we'll just plug it in. 3 times 2, -1 plus 1, and I hope at this point you can see why I chose to use 0 and -1. Right here you can see that -1 plus 1 gives me 0, which makes my calculations easier. That's just going to be 3 times 1, because it's 2 to the 0 power, plus 2, which is going to give me 5. Yeah. We'll plot that point, -1 and 5. That's about right there. Because I already know the shape of the graph, I can go ahead and kind of draw in this curve. If I didn't know the shape of the graph, then it would be really difficult for me to draw in that curve. That's not exactly straight, but you get the idea. If I knew the shape, I know exactly how it goes. I know what it can't pass. I know how it approaches the asymptote. I know how it goes up through the y-intercept and how it continues up. This is exponential growth. So in the behavior, if you want to talk about that, if you talk about on the right side, it's just going to be headed up always. That's what exponential growth does. And on the left side, it's always going to be going down right to that asymptote. It'll never cross it, but it'll get around pretty close to just touching it. So what you want to walk away from this with is, I need to be able to look at a graph, be able to find the asymptote, be able to find the y-intercept, and graph a few extra points so that I can get the curvature fairly close. 3 points would be probably optimal. I would do the y-intercept. I would do maybe 1 on either side of the y-axis. And that would give me a really good indication of where my graph is. Next example. We are going to look at something that we've done before. This is compound interest. P equals 1 plus r over n raised to the nt. Just to remind you, this is P is the principal. It's the amount of money that you invest to begin with. The R is your interest rate. N is the number of times it compounds. And that is it annually? Is it compound annually or semi-annually or every monthly, daily, or continuous? Of course, continuous uses a different formula. But those are the things that we studied. So to start with, we have invested $3,000 into an account. This account pays 6% interest. Be careful. Remember, when you use percentages, we always use the decimal value, 0.06, for our rate. Never use 6. If you use 6, it will be horribly wrong. It shouldn't make any sense that you would have that much money after so little time. It tells us that we're going to compound annually, which means once a year. So n is only going to be 1 in this problem. What we want to know is, I need to know t. I need to know how many years it's going to take before my amount doubles. So I'm looking to find when A is equal, amount, A is the amount in the account. So A is going to be basically $6,000. And so there's a number of ways we can do this. We've already explored this by exponentials, by solving the equation. We would plug it in like this: 6,000 equals 3,000 times 1 plus r to the n, r divided by n, raised to the n t. Let me actually put those values in. Plus 0.06 over 1 raised to the 1 times t. In this case, I could simplify and work it out, but I want to graph this and solve it graphically. And this would be a easy question to do by hand or using a calculator. Effectively, I really want to know what the value is at 0. So the equation that I'm going to be graphing is going to look like this: A equals 3,000 times 1.06 to the t power. So this is our traditional exponential graph. You've got it 3,000, that's your A. Your B is 1.06, so this is exponential growth because it's bigger than 1, raised to a variable, which that is time. So I could plug in a couple of values, and this is the values that I chose, and some of these are arbitrary. I did a little bit of research, plugged it in, found out which ones worked. So I chose 9, 0. 0 is easy because I started out at time 0, and that was at, so 1, 2, 3, 4, 5, 6, there's 6,000. So these are in thousands, so 1,000, 2,000, 3,000, 4,000. There we go. So 9,000, or 9 years into it, I have 5,068.4. I just rounded to the nearest tenth, and I went all the way to 12 next, and that was where I found that it went just over $6,000. And I was just plugging in whole numbers. I'm not looking to find the perfect value. I'm looking in terms of whole numbers. What year, during which year would I reach $6,000? And this is more than enough. 5, 6, 7, 8, 9, 10, 11, 12. So if I plot my original value here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's 9. That's 12. If I go up to 9, I'm up at 5,068. So it's about right here. And 12,000 was just over 6,000. And so, and this is definitely a slower interest rate. It's 1.06. So the amount of curvature is pretty slow. The actual asymptote is going to be down at 0 here, but we're not really interested in that part of the graph. What we wanted to know was this mark here. If we kind of go over, what we'll see is these lines kind of match up, and that was the value we were looking for. So a number of ways you can do this. Solving it algebraically, using your calculator to do. You'd end up having to do logarithms, which you may or not be familiar with or comfortable with. Another way of doing this is by plugging in values for t and just finding out what those values are. Plugged in 1, that definitely got you not very far. Plugged in 4 or 6 or 9, 10, 12, and you just basically wanted to know at which one did you actually end up having $6,000. So this example was really a trial and error kind of example. I didn't expect you to graph this with a decimal value just by hand. So make sure that you actually try your XY table and plot these, and this is definitely an estimated values. You can clearly see from my graph it's definitely not perfect. So make sure that you have got this formula down. It's in your book, is one of the examples, example 3 or 4. But if you haven't got that down, write it down now. And your homework assignment is going to be in, I think it's going to be the odd numbers in section 4.1, or actually there may be a homework sheet. Actually there is a sheet. So the sub should have a worksheet for you, or Miss Critch will have it for you. She should have given it to the sub, so check and hand out the worksheet now. So explore those, and we'll talk about that. Hopefully I'll be back tomorrow.